Hello, today I want to talk about the design of drone systems with Papyrus for robotics. And this work has been done in the context of the Comp for Drones project and previously in the European project Robotics, and there's also some work that has been done in ROS and DD. So why is the development of robotic systems still very challenging? Well, we have more and more functionalities, but its development is still in a craft stage. If you compare it with other domains such as automotive and avionics, there are numerous and incompatible component-based frameworks, even if that is getting better now, as we will see. There's still a lot of code-centric software development approach. So most algorithms are directly coded. And there is no standard interface between the different roles of the stakeholders that are involved in developing robotic systems, which requires different skills. So here you see some of the stakeholders in the lower part of these pictures. There is, for instance, a component design to be done. There's also some validation verification. Some implementation work with code generation. And that is why we said a model-driven approach is a good way to have a common umbrella for all these different activities. We have a data sheet that is providing information about the components that we are using and also the other artifacts. And we can combine this all in a common framework. So Papyrus for Robotics provides code generation for ROS. Why are we using ROS? Well, it's a set of software libraries that is very widely used in robotic applications. It has a lot of different things to offer. It's completely open source. ROS1 has already been started quite a long time ago in 2007, and ROS2 has a reduced footprint. It's based on standard middleware DDS that is very powerful, and therefore it's better suited for embedded real-time systems because DDS has quite a good support for quality of service, for instance. For very resource-constrained systems, you can use micro-ROS with some restrictions ROS2 compatible. So as a result, a growing number of companies migrate to ROS2, and Papyrus for Robotics supports code generation for ROS2. And this work has been chiefly done in the project ROS MDD, which is part of the ROS Industrial Project, European H2020 project. So Papyrus is based, Papyrus for Robotics is based on Papyrus, and Papyrus is an open source modeling-based engineering tool that supports standards from the Object Management Group, so notably UML, of course, but also some of the extensions such as Mark for the real-time. Here are some links where to get started with Papyrus in general. And then there's also Papyrus for Robotics, which is a customization for the robotics domain. And it makes use of this possibility in Papyrus to be customizable for a specific domain. Here I also have some links on the webpage from Papyrus for Robotics, some wiki documentation, and a YouTube channel. Here on this slide, you have an overview of the different activities. I won't go into detail because I will talk about each of these activities in the sequel. We have used Papyrus for robotics in our European projects. There is notably the Robotics project, which is about to end now after 4 years. What you see here is a pick-and-place application with the EasyBot robot, and we have used a high-level behavior tree specification to do that, and we will see some about these possibilities to use a behavior tree later on. On the right-hand side, you see a use case from the Comfort Drones project in which a parcel needs to be delivered from a distribution center to a customer. And there are different steps. In the first step, a drone is delivering the parcel to a rover. It has to land on the rover, and then the rover is delivering this parcel to the final customer. And well, this is a logistic use case we are working on. And in the context of this presentation, I will use a more simpler use case, just a patrolling drover use case to illustrate Papyrus for robotics. So when you start with Papyrus for robotics, it's good to have some service definitions. Service definitions are the definitions that a component provides or offers at its port, via its ports. And well, you have different interaction patterns, and here on the right-hand side, you see some data types that are already provided by the system, by Papyrus for robotics. And it's a good thing that you rarely have to start from scratch, because you have all these data types already defined in some model libraries. These have been obtained via reverse engineering from ROS2. And the good thing of using this kind of standardized service definition is that your components are likely to be compatible with others if they provide or require these standardized services. So here you see a flight control component. So an example of a component definition. What you see here is, on one hand, the possibility to parameterize a component. On the other hand, that some internal behaviors, so-called activities in Robotics, interact with the ports, get data from or deliver data to ports. Well, this is the view that you see when you're defining your components. We are now going more into details. What you see here is the Eclipse-based editor. You have in the center the diagram, this component diagram you have seen before. On the right-hand side, there is a palette which with all the options what you can do to make your model. And on the left-hand side, you see the Model Explorer. This contains all the artifacts of your model, also some of the imported libraries. Well, the difference between the Model Explorer and the diagram is not only that is, well, the diagram is a graphical view, but the difference is also that the Model Explorer is always complete. The diagram could just highlight some aspects you want to show. It does not need to be a complete picture. And finally, there's a property view, which allows you to see some details of selected elements. You can select either in the Model Explorer or in the diagram. So you can modify some of the properties. Interestingly, there's also a possibility to specify assertion and contracts in the context of safety. And we also have an Xtext editor, because some people might prefer to have a textual edition of these component definitions. So the next phase is the system build. You have done your components, and now you're assembling a system based on instances of existing components, and you have to do the wiring. So here you see our flight components we have seen before. There's also a mission management component, for instance, a flight management and flight planning component, but I won't go into detail of that. Now we are looking at task planning that is done by behavior developers. So you see there are different stakeholders involved. And with respect to task planning, it's good to know that Papyrus supports high-level tasks based on a formalism that is known as behavior tree. So you have a hierarchical decomposition of your behavior. you can have some fallback mechanisms or some queries inside this behavior tree execution. And this is particularly well suited for having complex tasks that have to react eventually to some changed environment condition. So what we want to do here is a petrol use case, which is a simpler variant of this delivery use case, in which a drone is just patrolling over a certain area. And of course, it has to make sure that it is always suitably charged, at least with some minimum battery level. And we could add a rule that whenever the battery level drops below 30%, we have to stop the current task and fly to a charging station. And that is specified here in this behavior tree. You see that there is here a condition, enough power, and then we are executing our normal task. And if this is no longer the case, we are going here in this fly to point section. We are flying to a charging station, and the drone is staying there until it is sufficiently charged. And there's also fallback behavior if this is not possible. So the sequencer executes here the skill and is interacting with the power management and the mission management components of the drone. What you see here is there are some skills involved of the robotic system, of the drone system. And here the behavior tree execution sequencer is interacting directly with these components that are exposing some of the skills of our drones. So notably here, the enough power and with options of the power management system. So the next task is the risk assessment executed by a safety engineer. And there's one activity that is quite important in this context, that is the hazard analysis and risk assessment, or short HARA, which is widely used in avionics and drones. You can see here an extract from a journal that appeared in 2015. You can see here an identification of some of the risk, and there is a qualitatively property if this risk is tolerable, unacceptable, or acceptable. And we also have some mitigation actions. And this analysis is not only recommended, but even demanded by some safety standards, such as the ISO 14121 to safety of machinery. It demands that you do a risk assessment for certain machines. So what does this mean for Papyrus for robotics? We have, for instance, the possibility to specify, well, we have in the context of having behavior trees, we can identify hazard, associate them with a skill, and assess their criticality. So an important part here is the association of a hazard with a skill. So for instance, the power management skill, the power level skill that you see here could have failures that it is not properly sensing the power, and for instance reporting a higher power state than it actually is, which in turn might imply that we are not going to a charging station, and then the drone might be damaged. There's another skill that is fly to point. we might have the problem that there is an incident during landing. The system might crash, which is not only harmful for the drone, but also harmful eventually for people. So you can see here some of these criticalities that are qualitatively associated with these events. And the advantage of associating these hazards with skill is that we can potentially reuse these when we are defining some high-level missions that are based on the same skills that we have used here. So finally, when all the artifacts are specified, we expect that the tool is generating some artifacts. And in case of Papyrus for robotics, it's generating build and launch files for ROS2. So these are package XML, CMake list files. It's also configuring Eclipse CDT to use Qualcomm, the build mechanism of ROS2. It also generates a launch script which contains some remappings. The remappings are used, for instance, if a component needs to talk to two different sensor instances, which are in principle of the same type. So as a single component definition is used, we have to make sure that the standard output topic here is remapped so that it gets to our control mechanism using this standard one. And for parameter configuration, we generate the YAML files of ROS2, and we also generate a launch script that optionally activates components automatically. There is integration with Eclipse, CDT, the C++ development tools. We can launch and debug a component from Eclipse. There's a video that you might want to have a look at. And we can also manage the Eclipse launch configuration and scripts. We have done some evaluation of the approach. It's mostly related to the reduction of the development effort, on one hand for the component development, on the other hand for the system integration. And I think the system integration is one, the advantages of having a model-driven approach are most important. When we are generating code for a component, we basically have the advantages and of the manual tasks like declaring publisher or consumer. It's less effort because there's less code to write. So we have a reduction of about 25% in the body files. It's much more important, the reduction is for the build files, because these are almost completely generated by our system. And I think the biggest advantage is that when we are writing our system, we have an improved quality and safety because we have this higher consistency as some of the artifacts are generated, and because we have this integration of a hazard and risk analysis. So here's an outlook of the roadmap. We are currently using Papyrus for robotic in several projects or European projects, so it continues to be developed actively. We have support for composites components in the future, so that we can also model hierarchically components and reuse them in more complex systems. There is an ongoing work that we are looking at a link to ROS2 based planning. So here is ROS2 based planning system, and with respect to real time, there is compositional scalability analysis with Python CPA and ROS2, and we have some ideas that we can already do some tests on a model level to do this compositional scalability analysis before the system is built. And this will also reduce the development effort as it provides an early feedback and eventually re-architecturing. Thank you for your attention.